So, hello to everybody, here we are, see the microphone is active and we go to our lecture. So, I already recorded this lecture, but at the end in the iPad there was nothing, so I have to repeat it, but the text is already written. So, again, the main message of this course is never buy iPad. Okay, let us go to... Let me verify again. Okay, microphone active. Okay, let us go to our... you see now it is recording. There is the red signal up there. So we are safe. So, so during the last lecture, I gave you two very important remarks. I recall you that we obtained these remarks through a particular example, to a particular exercise, but notwithstanding it, they are general. They apply to every field. So, first, we saw that it is an immediate computation that if f is a gradient field, then f is conservative. This is just a computation. But through another a bit more involved and also evolved reasoning, we found that if f is conservative, it is possible to construct a potential, so a function whose gradient equals f. So f is a gradient field. So being conservative is equivalent of being gradient field. We will go back to that point in the next lecture. Second, you start from field f, you obtain a potential u. This is not unique, but every other potential is the same u plus a real constant. Okay, so it is very simple. It is like when computing an indefinite integral, so the set of primitives. It is always the same function up to an updated constant, and here this is the same. Okay, and now I started to discuss with you this proposition that gives us another characterization of being conservative. F is conservative if and only if every circulation of f is zero. What is a circulation? So as you know from the course of geometry, there are curves that are closed. Closed means that they start from a point and they end up at the same point. The initial and the final point coincide. Okay, I don't want to insist on the properties, on regularities, and other things, on simplicity of and so on. This either you already know or, however, is quite useless for our purposes. So, circulation is just the name of the integral line on a closed curve. And in the symbol, in order to stress the fact that you are on a closed line, you put this circle on the sign of integral. Okay? So, we want to prove that being conservatives is equivalent to say that every circulation is zero. In order to prove that, consider a conservative field f and take a closed path gamma. Gamma here is the green one. Oh, sorry, it is in the other way around. Gamma is this guy here. Okay, we want to obtain that the integral of f on this generic, arbitrary closed path is zero. In order to prove that, consider 2 points on gamma distinct, so A and B. They are not the same point. And of course, then you can consider 2 curves which are parts of gamma. The first curve is gamma 1, going from A to B, following the same sense of gamma, gamma 1. The second is gamma 2, going from B to A, following the same sense of gamma. Okay? Of course, gamma is equal to gamma 1 union gamma 2, in the sense that if you run through gamma 1 and then through gamma 2 at the end, you run through the whole gamma. But because of this, the fact that gamma decomposes in this way, the line integral of a field f on gamma decomposes into the sum of the line integral of f on gamma 1 plus the line integral of f on gamma 2. Now, f is conservative. Let me write it here. F conservative, which means that f is gradient. Which means that there exists u function u such that f is the gradient of u. So now instead of f, write gradient of u. So the first integral is just rewritten here, and the second integral is just rewritten here. Just copied, but instead of f we wrote gradient of u. Now remember what happens when you integrate a gradient along a line. We already performed this computation, and we found that the final result is just the difference of the values of the potential between the end point and the initial point. So for gamma 1, let us go back to the picture. For gamma 1, the starting point is A and the final point is B. So the integral amounts to u of B minus u of A. For gamma 2, it is the contrary. The starting point is B and the end point is A. So the final result is u of A minus u of B. So here it is. U of A minus u of B. And these four guys cancel u of B minus u of B, u of A minus u of A. And so we obtain 0. The conclusion is that if f is conservative, then every circulation, so the circulation on every closed curve of the field, is equal to 0. This is very important. This is what you find in many books in physics when talking about conservative fields. Good. So, conservative fields for a work, for a, I don't know, electric force or gravitational force, means that the work made by the force when the charge or the point particle you are considering is moving on a closed line is 0. So now we want to prove the inverse. We want to prove that if on every circulation the line integral of the field is 0, then the field is conservative. Which means that, according to our definition, the integral on a line only depends on the initial and on the final point. So we start assuming as a hypothesis what we found at the end of the previous proof, the hypothesis that on every circulation, on every closed path, the circulation of f is 0. And then we consider two arbitrary points A and B in R3. And we have this very simple construction. We go from A to B through a path gamma 1. And then we also go from A to B through another path gamma 2. So you see the situation is a bit reversed with respect to what it was some minutes ago. Here we have two paths with the same initial and final point, but now we unify them to form gamma. So in order to unify them, we first go through gamma 1 in this way. Then we go through gamma 2, but in the opposite direction. Geometrically, the object is the same, but as a curve, as a parametrization, it is different because the direction has changed. So we cannot call it gamma 2 again, but minus gamma 2. Okay? Gamma is equal to gamma 1 unus minus gamma 2, where gamma 2 is the curve, not gamma 1, sorry, the curve gamma 2 run through in the opposite sense. And now we have two remarks that are in order. First, the first remark is that gamma is a closed path in the sense that we specified before. The initial point and the end point coincide. First. Second, this is very easy, just geometrical. Second is a bit more complicated, and it is the following. The line integral of f on gamma 2 is minus the line integral of f on minus gamma 2, so the same gamma 2, but runs through in the opposite direction. So let me give you first an easy argument, an intuitive argument. The argument is this one. Consider that this line, this red line, this is a curve, and we want to compute the quantity f dot dr, which is a sort of infinitesimal quantity that construct our line integral. Okay? So here we have f, f dot t, we fix on a point P. On this point P, the field is F, for instance, here. And dr, when moving in this direction, dr is this green vector here. But if we consider the other direction dr, the variation of r is the contrary, is the opposite with respect to the previous one. And of course, it is clear that the dot product f dot dr change in sign whether dr is this guy or this guy. So this is why when you sum all contribution of all points, the line integral of a field on a line depends on the direction. The absolute value of the result will be the same, but the sign changes. This is, I probably would have stressed better in the lecture when I talked about parametrization. But so the message is that when you reparameterize a curve, you have to be careful of not changing the sense of the sense of the curve. Otherwise, the absolute value of the integral will be the same, but the sign will change. Okay? So this is the intuition. Dr changes sign. And now let us go with a proof, with a mathematical proof. So remember, we are here. This is gamma 2. This is minus gamma 2. And now consider R of t as a parameterization of gamma 2. R of t with t in this interval, t naught, t1. So from this R of t, we easily obtain a parameterization of minus gamma 2, which I denoted by capital R of t, and it is simply R of minus t with t in the range minus t1 minus t naught. So this, of course, is a parameterization of minus gamma 2, because you see when t is equal to minus t1, R of t, R of minus t1, is R, small r, of minus minus t1. So it is R of t1, which is the final point of gamma 2, and so on. Now differentiate capital R of t, and by composition, by this minus here, you gain a minus here. But it is clear, this means that when you change the sense on your curve, the velocity changes sign. Velocity is a vector, so it changes sign. And now compute the line integral of f on minus gamma 2. According to the definition of line integral, this is the integral between the extreme of the parameterization of minus gamma 2, which are minus t1 minus t naught, dot product with the velocity on gamma 2 in the reverse sense. And then in the next passage, so let us see what happens. In the next passage, we first recall the definition of capital R of t, the parameterization of minus gamma t2. Here, we recall that the velocity is the same up to a sign which is here. Okay, this is the equivalent. And the extreme of integration remain the same. Second passage, in the second passage there is a change of variable. Let me cancel this notation that I made before. In the second passage there is a change of variable, and so we replace t with minus t, and so here we have that R of minus t becomes R of t, R dot of minus t becomes R dot of t, and it's okay. Minus dt becomes dt, because t becomes minus t, and here the extreme of integration change their sign. But now just exchange t0 and t1, exchange the extremes of integration, and so you gain a minus sign, but then a writing here which is exactly the line integral of f on gamma 2 in the original sense. So at the end, what you have is that line integral of minus gamma 2 is equal to minus the line integral of gamma 2, as we announced it. So this is the result. Okay? This is a general result, but now we want to apply this general result to our problem, the problem of proving this. So we have gamma, which is a circuit, so a closed curve, and we start by using the hypothesis that the circulation, every circulation of f is 0, but gamma is the union of gamma 1 and minus gamma 2. So the integral splits in the integral on gamma 1 plus the same line integral on minus gamma 2. Now the first term here remains the same, and in the second we use the result we just proved. So the line integral on minus gamma 2 is minus the line integral on gamma 2. So 0 is equal to the difference of these two objects, which means that these two objects are the same. The line integral on gamma 1 is equal to the line integral on gamma 2. But what are gamma 1 and gamma 2? They are two arbitrarily chosen paths joining the two arbitrarily chosen points A and B. The fact that the integral on these two paths is the same means that for every couple of points, the line integral of f along a line joining the 2 points is independent of the particular path followed. Only depends on the 2 points, the final and the initial. So, as a consequence, f is conservative by the very definition we gave of conservative field. So I think we can close this lecture by recalling the different notions of conservativity we had by this theorem. I put them as a theorem, equivalent notion of conservativity. So we have f from omega to R3, where omega is a region in the three-dimensional space. It can coincide with R3. But here I want to start stressing the domain, because in the next lecture the domain will start having some relevance. First, definition. Given two arbitrary points A and B in omega, the integral of f along a curve joining A and B does not depend on the chosen curve. Okay? It is not important the path, it is important from where you start and where you get. Second, given an arbitrary closed curve in omega, the circulation of the field f on the curve is always 0. Third, f is a gradient. So there exists a function u, which is called a potential, from omega to R3, such that f of x is the gradient of u. The three are equivalent definition of conservative fields. You can use whatever you want, and also it depends on book. And I want also to recall you how to, given a conservative field, the question is how to obtain a potential. And this is exactly how we did. So fix a point where your potential will be equal to 0, and take another point x, y, z. Consider it as fixed, but of course, when you will take another point x, y, z, the computation will be the same. And then you want to integrate your field on a path starting from P and arriving at x point z, x, y, z. Since the field is conservative, you can choose this path as you want. We chose a broken line like that in our previous example, because it was very simple. So take the path that simplifies at best the computations. So what you obtain at the end of the formula is that u, x, y, z will be equal to the integral of f, the line integral of f from the point P, for instance the origin, up to the point x, y, z. So as made in the exercise, we have that f turns out that if you compute the gradient of u, then you find f. Okay, bye. I hope that everything is perfect.